So let's begin the second part of the talk, which is about G2 geometry. G2 geometry is the study of G2 structures on 7 manifolds. And we're going to be interested specifically in how G2 structures on 7 manifolds relate to G2 holonomy metrics on 7 manifolds. But before we can do any of that, we're going to need to introduce some linear algebra, I should really say exceptional linear algebra, relating to the Octonians, and we'll put this in the general context of norm division algebras. Okay, so why the Octonians? Well, it's because the Lie group G2 is intimately related to the Octonians. There are a couple of links. Here's one. Let's say A is a norm division algebra. I'll define that in a minute. And consider its automorphism group, the set of invertible linear maps that preserve multiplication. Then the automorphism group of the real numbers is just the identity. That of the complex numbers is Z mod 2. The quaternions is SO3. But the automorphism group of the Octonians is exactly the compact exceptional Lie group G2. So if you like, you can take this as the definition of G2. Okay, G2 as the automorphism group of the Octonians. Okay, but we're going to take a slightly different approach, but let's first put this in the general setting of norm division algebras. So the point is, to understand G2, we definitely need to understand the Octonians a little better. So for us, a norm division algebra is a pair, A and an inner product, where A is a finite dimensional real algebra, not necessarily associative, not necessarily commutative, with a unit called 1, and the angle brackets will denote a positive definite inner product, and the norm has to respect multiplication. So that's how the two structures are intertwined. Okay, some notation. Let's let real of A denote the span of the element 1, so that's a line, and let im of A denote its orthogonal complement. So we can decompose A into real and imaginary, where again the real part is one-dimensional and the imaginary part is kind of the orthogonal complement. So you can write any element x as its real part plus its imaginary part, and you can define its conjugate as real part minus imaginary part. And for the most part, this works the way you would expect. The real part is 1/2 x plus x bar, and the imaginary part is 1/2 x minus x bar. But you have to be just a little careful because the conjugate of xy is the conjugate of y times the conjugate of x. And remember, the multiplication is not necessarily commutative, so you do have to worry about this a little bit. Here are some identities which are useful, very important actually when you deal with norm division algebra. You can pull out multiplication from inner products in a certain sense. And if x and y are orthogonal, then xy bar is negative yx bar. And I should emphasize that although norm division algebras are not necessarily associative, they do have a weak form of associativity called alternativity. And what that basically means is that multiplication is associative when two of the three elements are the same. So xy is just xxy regardless of the parentheses because we have two x's, I guess. Okay. So what we'd like to do is start with a norm division algebra and generate new norm division algebras, a larger one. And the inspiration for doing this comes from the following fact. If you have, that should say norm division algebra, if you have B is a norm division algebra and A is a norm division subalgebra containing the unit, and you choose epsilon to be an element of the orthogonal complement of unit length, then A epsilon is a perp, and there's this interesting looking multiplication law. And this multiplication law kind of inspires this construction called the Cayley-Dickson process, in which we can take a norm division algebra and build a bigger one. So what we're going to do basically is invert this fact. Okay, we're going to invert this fact. So let me be more precise. If you have a norm division algebra A, let's define B to be A plus A or A times A with this multiplication mentioned on the previous slide. And you can give this a positive definite inner product like so. And we'll call B the Cayley-Dickson extension of A. Okay, we can think of A as sitting inside B in the way you would think, just send a to a comma 0. And you can define epsilon to be the element 0, 1, and you can check that it squares to -1. And so every a comma b in the Cayley-Dickson extension can be written as a plus b epsilon, where again epsilon squares to -1. Note that we are not claiming yet that b is normed. This is an algebra, and it does have a positive definite inner product, but a priori we're not claiming that the norm actually respects multiplication. Okay, so what is this good for? So it turns out this is exactly the process by which you get the complex numbers, right? If you apply the Cayley-Dickson process to R, you get exactly C, right? This is where the complex numbers come from. And then you can do it again. You can apply the Cayley-Dickson process to C and get H, the quaternions, and then do it one more time. You apply the Cayley-Dickson process to H, the quaternions, and you get O, the octonians. And you might think that this process goes on forever, but it doesn't. Basically, every time you do the Cayley-Dickson process, you lose some nice algebraic property. So the theorem is this: if B is the Cayley-Dickson extension of a norm division algebra A, then B is normed if and only if A is associative. But B is associative if and only if A is commutative, and B is commutative if and only if A is the real numbers. So these three facts really greatly limit the space of all norm division algebras in a really significant way. There's only 4 of them. So this is sometimes called Herwitz's theorem. The only norm division algebras are the real numbers, the complex numbers, the quaternions, and the octonians. So if you like, the octonians are the unique non-associative norm division algebra over the real numbers. I should point out that some authors allow for a more general concept called a composition algebra, where the inner product is simply non-degenerate, not simply positive definite. And in that case, if you look at those classifications, you'll get 3 more. You'll get the split complex numbers, the split quaternions, and the split octonians. But we're just going to be assuming everything is positive definite. Okay, so we're going to be focusing on the octonians, which we're thinking of as a copy of R8. Let's split it into real and imaginary parts. So we have a real line, and its orthogonal complement, the imaginary octonians, is a copy of R7. So the imaginary octonians, R7, has some very interesting geometric structure, or linear algebraic structure, I guess. So one thing it supports is a vector cross product. Okay, so it's this map here, x cross y, given essentially as the commutator 1/2 xy minus yx, which is the same thing as negative of the imaginary part of yx. And this is a vector cross product in the sense that this map is skew symmetric. And if you do x cross y, that's orthogonal to x. It's also orthogonal to y. And the length of x cross y is the area of the parallelogram spanned by x and y. I should point out that vector cross products are very rare, and in fact they really only occur in dimensions 1, 3, and 7, where I guess the one-dimensional one is sort of trivial. And that's not a coincidence. This is because they're related to the norm division algebras, the real numbers, complex, quaternions, and octonians. So this cross product right here, this is the so-called 7-dimensional cross product, right? It's sort of analogous somehow to the usual cross product in R3. That one arises from the quaternions, the imaginary quaternions. This one arises from the imaginary octonians. Okay, we can encode this vector cross product as a 3 form, essentially by lowering an index, right? So using the metric, this 3 form, phi 0, is called the associative 3 form. It's essentially the same information after using the metric as the vector cross product. So here's an analogy which is actually quite useful and in fact very influential in G2 geometry. So let's think of a more familiar setting of the complex numbers, which we can think of as R2n. So in that case, we have a 2 form called the Kähler 2 form, omega of xy. It's the inner product of jx with y. And the analogy is that somehow this pair, j omega, is analogous to the cross product and the associative 3 form. J, the complex structure, is somehow similar to the cross product, and the Kähler form is somehow very similar to the associative 3 form. Okay, this analogy shouldn't be taken too literally. There are definitely some important differences, but it has motivated a lot of progress, or a lot of ideas at least, in the field. So the point is, we can think of the cross product as somehow an octonionic version of J, and we can think of phi 0 as an octonionic version, or imaginary octonionic version of the Kähler form. Okay, so you might ask, what does this look like in a basis? It's maybe not that pretty. So if you let 1, E1 through E7 be the standard basis of the Octonians, R8, then phi 0, the associative 3 form, is this right here, E123 plus E145, etc., where here EIJK is the wedge product of EI, wedge EJ, wedge EK. Every G2 geometer knows this formula, or has their own convention, at least, for the basis that gives phi 0. And these numbers are not random. They are essentially exactly the Octonionic multiplication table. In other words, E1 times E2 is E3, and E1 times E4 is E5. E4 times E5 is E1, etc. So if you know phi 0, that completely gives you the Octonionic multiplication table, and vice versa. Okay, so you might ask, is phi 0 in some sense special in the space of all 3 forms? How should we think of phi 0 as sort of sitting inside the space of all 3 forms? Is there anything kind of remarkable about it? And in fact, there is. So let's let V be R7, just for the sake of notation. And for each 3 form gamma on V, let's define this weird symmetric bilinear form B gamma as 1/6 hook. This is the hook right here, X hook gamma, wedge, Y hook gamma, wedge gamma. And let's say that gamma is definite if B gamma is definite. And we'll consider, we'll let lambda 3 plus denote the set of all definite 3 forms inside lambda 3. Okay, notice that if gamma is definite, then B gamma of xy, that's going to be some sort of 7 form. So it's going to be some number times sort of a generator. And so basically, if you have a definite 3 form, that gives you a positive definite inner product, G gamma, and an orientation form, vol gamma on R7. And so the quintessential example, or for us the important example of a definite 3 form, is phi 0. Okay, so let's think about the change of coordinate action on R7. So the GL7R action on R7. This induces a GL7R action on the space of 3 forms just by change of coordinates, or pullback. And the fundamental facts about this action and phi 0 really are these. Let's let phi 0 again be the associative 3 form. Then the orbit of phi 0 under this action is exactly the set of definite 3 forms. Okay, so in other words, if you sort of consider all the forms obtained from taking phi 0 and just changing coordinates, you get exactly the definite 3 forms. And the other fact, which is really fundamental to G2 geometry, is that the stabilizer of phi 0 under this action is G2. So this gives another link between G2 and the Octonian. So G2 is precisely the set of, if you want, 7x7 matrices, or linear transformations that preserve phi 0. This is somehow analogous to the definition of the unitary group as the set of linear transformations that preserve J and omega. Right? But here, just preserving phi 0 is enough to get the structure. And so, G2 geometers usually regard this equality, this is an observation often known as Bryans Theorem, although I think Robert Bryant would probably say this was known earlier. This is often regarded as sort of the working definition of the Lie group G2. This is very fundamental to the subject. So if you count dimensions, right, the space of 3 forms is 35 dimensional, and G2 is a 14-dimensional Lie group, and you apply the orbit stabilizer theorem, then what you discover is sort of this, almost like an arithmetic accident in a way. The orbit of phi 0, which is the set of definite 3 forms, is an open set. in the space of all three forms, and that's a very fundamental fact. What that means is if you perturb phi0 a little bit, you'll still get a definite three form. This is a very rare property. There are very few open orbits in sort of the set of K forms on a vector space, and I believe they're classified, in fact. Okay, so that's all linear algebra. In a sense, what we just discussed was the flat model of what we now want to discuss, which is, of course, manifolds. So what we want to do is discuss manifolds whose tangent spaces have the structure that we just talked about. So let's be more precise. Let's say M is a smooth 7 manifold. A G2 structure on M is a definite 3 form. Okay, so this is what a G2 structure is for us. It's a definite 3 form. And what I mean by that is that at each point, phi at x is a definite 3 form. So in other words, unwinding the definition, at each point x, this symmetric bilinear form is definite. But by what we said before about how the definite 3 forms is really the orbit of phi0, there's an equivalent characterization. Okay, so all of these conditions are equivalent. You can say that a G2 structure is a 3 form such that at each point there's an isomorphism between the tangent space and R7, such that when you pull back the associative 3 form, the flat one, phi0, you get phi at x. Okay, or yet another way of saying this, for each point there exists a frame, okay, at that point, such that phi written in terms of that frame is exactly the flat model. So the way I like to think about this is this. Here's sort of the intuition. What a G2 structure does is it identifies the tangent spaces of your 7 manifold with the imaginary Octonians. So each tangent space is somehow a copy of the imaginary Octonians, and under this identification, the 3 form that defines the G2 structure, that looks like, it looks like the flat model phi0. This should be regular phi0 here. Okay, so let's say you have a smooth 7 manifold. So by what we said before about how a definite 3 form gives you a metric and an orientation, well, if you have a G2 structure on a 7 manifold, you automatically get a metric on your manifold and an orientation. Okay, and these satisfy these formulas right here. Okay, but a few things to note. First of all, the correspondence which sends a G2 structure to a metric is not injective. And what that means is that different G2 structures on a 7 manifold can induce the same metric. Okay, moreover, this map sending a G2 structure to a metric, to its induced metric, this is a highly nonlinear map, which is somehow a very big difference from the situation in Kähler geometry. Moreover, the Hodge star is determined from the metric and the orientation, which itself depends nonlinearly on phi. So really, when you see star phi, there's somehow a nonlinear kind of dependence going on here. Okay, so you might ask which 7 manifolds admit a G2 structure. This is a purely topological question. It's kind of like asking which manifolds admit an almost complex structure, right? That can be answered purely in terms of characteristic classes, right? So a 7 manifold admits a G2 structure if and only if it is orientable in spin, meaning that the first 2 Stiefel-Whitney classes vanish. Okay, so what we're really interested in is G2 holonomy metrics. Okay, we'd like to know how does all of this machinery, how do G2 structures on 7 manifolds relate to G2 holonomy metrics? And to answer this, we need to introduce some classes of G2 structures. Okay, so finally we're introducing some calculus or some analysis. Right now, everything up to this point has really been linear algebra. So let's say phi is a G2 structure always on a 7 manifold. Say phi is closed if phi is closed, if d phi is 0. And say phi is co-closed if it's co-closed, if d of star phi is 0. Okay, and the question of which 7 manifolds admit a closed G2 structure, that is open. Right? We don't know which 7 manifolds admit a closed G2 structure. We also don't know which 7 manifolds admit a co-closed G2 structure. And in fact, the classes of 7 manifolds that admit a closed G2 structure and those that admit a co-closed structure are believed to be really radically different. Okay, and we're going to be interested in the intersection of those, so we're really interested in this condition called torsion-free. Say that phi is torsion-free if it is both closed and co-closed. Okay, and the reason we care about this is explained by the following theorem of Fernandez and Gray. Let's say M is orientable spin 7-manifold. If you have a G2 structure that's torsion-free, meaning it's closed and co-closed, then its induced metric has holonomy contained in G2. Conversely, every metric whose holonomy is contained in G2 arises in this way. So if you have a metric G, just any metric, and its holonomy is equal to G2 or contained in G2, then that metric must arise as the induced metric of a G2 structure, where that G2 structure is torsion-free, closed and co-closed. So you might say, okay, but I want the holonomy to equal G2. I want to get G2 on the nose. So fortunately, there are two very useful criteria for getting equality here. Okay, one of them is due to Robert Bryant. So if you have a simply connected 7-manifold and you know that your holonomy is contained in G2, then in fact you get equality if and only if there are no parallel 1 forms aside from the 0 1 form. A different criterion is due to Dominic Joyce, which says that if you have a compact 7-manifold, not necessarily simply connected, and the holonomy is contained in G2, then you get equality if and only if the fundamental group is finite. Okay, the proof of Bryant's criterion, if I remember correctly, is an application of Berger's list together with the holonomy principle mentioned earlier, whereas Joyce's criterion is also an appeal to Berger's list together with I believe, the Cheeger-Gromall splitting theorem. Okay, so this slide suggests a strategy, in fact, really the only strategy we have at the moment for constructing metrics with holonomy equal to G2. So the strategy we have is this. Step 1 is you construct a torsion-free G2 structure. That's not easy. That amounts to solving a nonlinear PDE system. Okay, this system right here of you want the G2 structure to be closed and co-closed. But if you're able to do this, then you get a metric whose holonomy is contained in G2. And then to get equality, you can, in the simply connected case, apply Bryant's criterion, or in the compact case, you can apply Joyce's criterion, and then you're good. Okay, so I should point out that something maybe I could have said earlier is that in the compact case, there are several topological obstructions are known to the existence of G2 holonomy metrics. For example, as mentioned on the previous slide, the fundamental group has to be finite. The third Betti number has to be at least 1, so meaning it can't be 0. And the first Pondriagin class has to be non-zero. And it's a difficult open problem to find necessary and sufficient conditions for a 7-manifold to admit G2 holonomy metrics. So we don't have anything like Yao's solution of the Calabi conjecture, some sort of Calabi-Yau type criterion that would tell us, if you have a compact orientable spin manifold, when does it admit G2 holonomy metrics? This is a very, very difficult open problem. Okay. So in the rest of the talk, I'd like to give some examples, just a few examples of 7-manifolds with G2 holonomy, and I'll mention some constructions that have historically been important. And very briefly, I'd like to comment on some interactions that G2 geometry enjoys with calibrated geometry. That's a subset of the study of minimal submanifolds. And very quickly, I'll mention some interactions with gauge theory and kind of mention some conjectures on how these two subareas are interrelated.